Let's take a look at Kirchoff's rules, which help us analyze complex circuitry. Gustav Kirchoff developed a set of rules in the mid-19th century that guided complex circuitry. Kirchoff's first rule is known as the junction rule. This says that at any junction, also called a node, or where there is an intersection of wires, the sum of all the currents entering the junction is equal to the sum of all the currents leaving the junction. It also can be stated as the current coming into a junction is equal to the current going out of the junction because there will be no accumulation of charge. As you can see in the diagram, we have a current 1 entering the junction, current 2 coming into the junction as well, and current 3 leaving the junction. The amount in is going to be equal to the amount out at that junction. This demonstrates the law of conservation of electric charge. The second rule is known as the loop rule. This states that the sum of the changes in potential around any closed path of the circuit must be 0. Simply stated, the total voltage in any closed loop is equal to 0. This rule is essentially a statement of the law of conservation of energy, because the voltage is directly related to the amount of energy that charge carries. As we can see in the circuit diagram, the current moves in a counterclockwise fashion. From our knowledge of simple circuits, a potential difference exists within the battery, and charge gains energy as a result of the chemical reaction produced. Current begins to flow through the wire, and as the charge enters the resistor, the charge loses energy. Because the charge must carry no energy by the time it returns to the battery, the energy lost in the resistor must be equal to the gain in energy through the battery. If there are multiple resistors in a given loop, then the total loss of energy through all the resistors is equal to the total gain in energy through the battery. There are a few conventions that must be used when working with the loop rule. The potential difference or voltage across a battery will be considered positive if moving from the negative terminal to the positive terminal. A negative voltage should be used if moving from the positive terminal to the negative terminal. In any resistor, the voltage should be considered negative. Let's take a look at an example. In the diagram shown, we have a complex circuit which involves 2 batteries and 3 resistors. We can only analyze this circuit using Kirchoff's rules. We begin with Kirchoff's first rule, the junction rule, using the junction at the top of the circuit as shown here by the red dot. Current 1 enters the junction, current 2 enters the junction, and current 3 leaves the junction. The junction rule can then be written as I1 plus I2 equals I3, or the current into the junction is equal to the current coming out of the junction. We can then use Kirchoff's loop rule to form expressions for the 2 separate loops shown in the circuit diagram. We will consider the loop on the left, loop 1. We can draw in an arrow to represent the direction in which we are going to analyze this circuit, or, if one is given, we can use the suggested direction. Please note, this is an arbitrary direction used to analyze the circuit. It does not have to follow the direction of the current. Because we are analyzing loop 1 in a clockwise fashion, I will begin with the battery. You can select any starting point. The battery is given a voltage V1, and because we are moving from the negative terminal to the positive terminal of the battery, we will call this voltage positive V1. Continuing on through the circuit, we then meet resistor R1. by convention, the voltage across a resistor is considered negative. So we will write this as minus V sub R1, meaning the voltage across resistor 1. Then continuing through the circuit, we hit resistor 3, which again, by convention, is considered a negative voltage. So we write this as minus V sub R3, meaning the voltage across resistor 3. Finally, we set the sum of these voltages equal to 0. We are finished with the first loop. We can analyze loop 2 given the arbitrary error. I will again begin with the battery, but we can choose any starting point. Because we're moving from the negative terminal of the battery to the positive terminal, we will consider the voltage positive. We then hit resistor R2, and we will call this minus V sub R2. And finally, we finish with resistor 3, which we will call minus V sub R3. The sum of these voltages is set equal to 0. We now have 3 useful equations. Let's see how these might be used in a problem. In this problem, we will use the exact same circuit diagram as the one on the previous slide. In this problem, we will assume the voltage across the battery in loop 1, which we will call V1, is 10 volts. The voltage across the battery in loop 2, V2, will be 20 volts. Resistor 1 will have a resistance of 10 ohms, resistor 2 a resistance of 20 ohms, and resistor 3 40 ohms. Our questions are, what is the current in each branch of the wire, and what is the potential drop across resistors? Using Kirchoff's rules, we create a set of equations. The first equation comes from the junction rule. We do not know any of the currents into or out of the junction, so we cannot alter the equation further. For the second equation, we use the loop rule for loop 1. We can insert 10 volts for V1, the voltage across the battery. We do not know the voltage across resistor 2, but we can insert the Ohm's law formula, V equals IR, where the current is I1 and the resistance is 10 ohms. Notice, we call this voltage negative because it is a resistor. We do not know the voltage across resistor 3, so we plug in the Ohm's law formula again, V equals IR, where the current I3 and the resistance is 40 ohms. This is then set equal to 0. It is very important to note at this point that if the direction of the current was opposite the direction that we are moving as we analyze the circuit through the loop, then we would need to negate the current. But in this case, the direction we are choosing to analyze the circuit with our drawn arrow is the direction of the current. So we will call the current positive. The negative sign in front of I1 and I3 comes from the fact that the voltage is considered negative across a resistor, not because of the direction of the current. Next, our third equation comes again from the loop rule, but for loop 2. We insert 20 volts for V2. We call this positive because we're moving from the negative terminal to the positive terminal of a battery. For resistor 2, we do not know the voltage, so we insert I2 times 20 ohms from the equation V equals IR. Again, we keep the minus sign out front because across a resistor, we call the voltage negative. And for resistor 3, we do not know the voltage, so